Swayam Prabha. Digital India. Educated India.
Hello and welcome to the discussion of a new topic in our course of Mechanics of Materials, and that is the topic of shear in beams. Now we have looked at shear previously. We have looked at shear with respect to the pulling and the pushing forces in nuts and bolts with respect to torsion and so on. But now we are going to solely focus on that when we have beams subjected to loading, bending moment and so on, how do the shears evolve? What is the nature of these different kinds of shears? So let's just go ahead and dive right into that. Now, as I said that before we look into the shear forces in beams, let's just go back and take a peek about what we saw essentially for shear when we talked about some of the other kinds of structures like nuts and bolts and so on. So if you remember from our discussion in the very initial days of our of this course of solid mechanics, we had in the first chapter when we were getting ourselves introduced to the different kinds of stresses like normal stresses, what are normal stresses, what are shear stresses. We have also seen some examples of these kinds of shear stresses which are there. For example, you will recall that these examples of double shear which we had looked at, or for single shear, it doesn't really matter. So the main focus is that we have been exposed to this guy tau over here. Remember that shear stresses were always expressed in terms of tau and the forces typically in terms of V. That's why when you come over here, you see that at this interface, at these junctures that we have over here, this is where the shear force acts. It always acts along the face, right? So if we have this bolt, it always acts along that face which is there. And since it acts along the face, this force V that you see over here acting along the face, it acts over this area that you see for the bolt. And if this is A over here, then this guy tau, as we remember, or if you remember even more clearly, we said that it is in some sense the average shear which we are talking about. And in this chapter we will understand why it is called average. So we had seen that your tau average was equals to V, that is the force. Remember, stress is always force divided by the area. It was V divided by A, right? The total shear force divided by the total area which is there. And also remember, it is the tau average, and we will see that how these assumptions sort of falls apart, that there is nothing called an average shear. It is good for our understanding, but the actual stress distribution is actually slightly more involved. So we had also seen like the single shear in a similar kind of a concept where we were having failure about say this particular plane, and tau was again V divided by A. Now in addition to these aspects, we have also learned one very important thing which is going to be extremely crucial when we talk about shear forces in beams. That is the principle of complementarity. If you remember that if we have a small element within a body, if we separate out a small chunk of an element, and if it has tau on one particular face, that automatically gives rise to the tau in all the other faces, just to maintain equilibrium, just to maintain the balance of the forces and the moments. And so that is the complementarity part, that it gives rise to shears in all the faces, and that the shear forces are one and the same. And we had derived this, that if you have a small body, right, and if we have the stresses as tau 1, tau 2, and equal and opposite stresses on the other side, through the balancing of the forces and the balancing of the moment, we have seen that tau 1 becomes equals to tau 2. So essentially the stresses that we have in these faces, they are equal and opposite. So that was the principle of complementarity that we have over here. Now with these two fundamental understandings, first of all the shear stress tau, and that if we take a small element within a body, it is complementary in the sense that if you have a shear stress along one of the faces, across all the four faces you are going to have shears. With these understandings, let's go ahead and try to understand that how shear forces act in beams, and you will be very intrigued at how the shear force acts. Now this is what we are looking at in beams, and we had seen this figure also when we were studying bending, although in that case we were focused on this, the bending moment over here. But as a result, so this is a cantilever beam, and as a result of this force P, if you cut a section somewhere, you know this now because you are experts at drawing shear force diagrams and bending moment diagrams. Or any section X at any distance X, we have the moment M and the shear force V. Now until now, when the previous topic on pure bending, we have already seen that how the moment, what kind of stresses, what kind of strains that sigma equals to my by I, what kind of stresses that it invokes, right? Now in this chapter, we are particularly going to focus on this guy over here, the shear stress, the shear force V. Now so you have something like this, right? So we have the bending momentum, which we're going to ignore for the time being because we are only dealing with shear over here. So you see that what we had sort of deciphered. So you have this force V over here, and as a result of V, remember again that concept of, or that sort of arbitrary concept of the tau average, that is this V, this force V divided by the cross-sectional area A. So this is this tau which is acting over here. Now here you see that this particular direction is your longitudinal direction, that is along the length of the beam that we have. So this is, let me write this down, longitudinal, and this direction is transverse. So what you are seeing is transverse, right? So this shear force, this V, and this tau is acting along the transverse direction. That is, when you're slicing that particular material that is there, when you're slicing it, so across this face, the shear force that is acting, that is the V which is acting over here. So divided by A that you see over here, that is going to give your average shear stress. So, but the question here is that, does this V only cause a transverse stress? Logically, yes. Logically, from what you see in the figure, is that this is a force V which is acting all across this face, or in this figure all across this face. So this tau only gives rise to this particular shear over here. But then let me show you some experiments which can be done, and you can do this, you can do these kinds of experiments at home as well. So let me just take you to that one over here. If you have, say this is the case where you have maybe 3 or 4 boards which are two distinct cases. In one case the boards are glued together, so essentially you have at these interfaces that you see, you have some amount of glue throughout running, and here as well, right? And you have another case where the boards are not glued together. So when you don't have the glue over here, if you're applying a particular force P over here, as a consequence of that, and you can do this at home as well, if you take 3 or 4 those wooden scales, and if you support them at the ends and then you apply a force at the center, you will see that, and if you have not glued those boards, you will see they're going to kind of stick out of each other. You can do it with a sheaf of paper as well. They are going to have some amount of sticking out, right? And this is the case when they're not glued. So when they are glued, the board still has the tendency of sort of sliding from one and the other. So you have this sliding kind of a phenomena. So what this glue is essentially doing, it is resisting at the interface of these boards. It is resisting some kind of force. That's why the glue is able to stick things together in place and have this beam beautifully bend like this. So you see, you're somehow getting a hint that your moment and your shears are sort of kind of related over here, right? So here you're allowing the boards, or the particle boards, to shift with respect to one another, and here the glue is resisting some amount of force along this particular direction. And what is this direction? Remember, this particular direction that you're looking at, it is actually the longitudinal direction, right? So it is resisting some amount of force in the longitudinal direction to keep all the boards together and bending in a kind of a uniform manner, right? So if you want to look at an experiment, this is done in the lab over here. So similar kind of, you have a support at the two ends, and you have a kind of a point load at the center. So you see over here how the boards are sticking out, are sort of sliding from one another. So what does that tell you? So that kind of tells you is that although you have this stress which is in the transverse direction, which is in this particular direction, which we call the transverse direction over here, right? You also develop because of complementarity. Remember what we discussed in complementarity, that if we take a small element and if you have tau in one of the faces, you are going to have tau in across all the four faces over there. Because of this force, you have this tau over here, and as a result, as a consequence of complementarity, you will have a tau here. You will have a tau on the back side face, at the bottom face as well. This is not shown over here. So because of this is the tau, this is the shear force, which is essentially acting as all these interfaces, which is resisted by this glue which you are seeing over here. So it is not only transverse shear. When the shear force is acting across the face of this member of this beam over here, as and when it is, as and when it is bending, you have shear which is running across this longitudinal axis as well. So shear is not just transverse. Because of the complementarity condition, it is as well as it is longitudinal shear as well. So let's take a bit more look into that one over here. So that means here complementary shear coexists. See, this is the complementary. What you saw over here, you see this guy is this tau over here. Now you cannot simply just have this tau, because you have to balance it with a tau over here, this tau and this tau, and if you resolve it into forces, you multiply with the face areas, you will have forces, equal and opposite forces separated by a distance. It will cause a couple, and that has to be resisted by this and this over here. So essentially this tau gives rise to all of this tau over here. They're all friends, they coexist, they live together. And what these particle boards are experienced, like see here, you don't see that them separating out. Why? Because this is one single material. But if you consider this whole sponge that you see over here, it is small strips, right? Each of these strips, when I'm bending it, each of these strips are also resisting this longitudinal shear as well. So essentially that brings me to tell you that once you have, so this is the face of the beam that you see over here, and when you are having a transverse shear, see this is the transverse shear, this is the transverse direction. So let's just mark it again. So this is the direction of the transverse and this is the direction of the longitudinal, right? So when you have the transverse shear, because of complementarity, as a result of the transverse shear force, you will have the transverse shear stress, which is this guy over here, and because of complementarity, you will have a shear stress along this direction as well. This is your longitudinal shear stress, and this one is your transverse shear stress that you're looking at over here, right? So I hope that you have grasped this concept, because this concept is going to be fundamental in deriving what is known as the very important shear formula, and when we look at some of the other aspects of shear as well in later chapters. So all you need to remember is that shear forces acting on a cross section does not simply result in shear stresses only in the cross section. It gives rise to shear stresses along the longitudinal axis as well, or in essence transverse and longitudinal shear stresses, they coexist with one another. Also, one more thing I want you to note before you go is that it's very interesting. You see here the length of the arrows, you see towards the center, the length of the arrows are longer than towards the edges. What's the reason for that? We had always talked about the tau equals to tau average, that is V divided by A. If it's an average sense, then the length of the arrows, if they're representative of the magnitude of this, should be same throughout. So these arrows also kind of tell you that the shear stresses are varying across the depth of the cross section, and in the upcoming lectures we will see why it varies and how is the variation depending upon the nature of the cross section that we have. In this lecture we will derive the shear formula. Now we have already seen one very important thing, that is, if you take a beam and you are computing the stresses at the interface, right, at any particular cross section in the beam, what we have seen that the shear stresses arise on the interface, that is fine because your applied load is acting at the interface, but at the same time this transverse shear stress also gives rise to a longitudinal shear stress at every single cross section that you have, at every single point. If you traverse across this section, at every single point, whatever is the tau going down, you have a complementary shear stress which is acting along the longitudinal axis. Now, to derive the shear formula, which essentially gives you a relationship between the tau, the shear stress, and the applied shear V, we are going to cheat. we are not going to consider the shear stress which is acting on this particular cross section over here, but the complementary shear which acts along here. So let's go ahead and see how to derive the shear formula that is there. Okay? So what you see here, let's just go through the figure first, the different components of the figure before we start writing down the different equations and coming up with the shear formula that is there. Now what you see in the screen is that you have this particular beam that is there, right? So this beam is under a varied set of loading. You have a UDL, you have some point loads, you have some point moments, and so on. Now as a result of these loads that you see over here, I have taken a small cross section. So let's say that this is a particular cross section this is a cross section of interest which you're looking at, which is shown somewhat over here. So this cross section over here is subjected to a variety of forces. As you can see that this is your neutral axis where you have, so this cross section undergoes bending, and as a result of which you will have, this is your neutral axis, say, right? And on one side, remember when we took that small beam element, we had m on one side, m plus dm on the other side, v on one side, v plus dv on the other side. Well, you don't see the v over here because you will see when we write the equilibrium equations, we are primarily considering fx equals to 0. The v and the small w, that is the UDL that you see in this over here, it acts vertically down. So that is ignored in this case because we are primarily interested in the x direction forces. Now let's take a look at the forces. Now this one, see, on any particular side, this due to this moment m, you have these stresses which are acting, which is sigma equals to my by I, and here also your sigma, if you call the sigma prime on this face, it is m plus dm times y divided by I. Now this gives rise to, say, compressive part at the top, zero stresses at the neutral axis, tensile at the bottom over here. So you have if you just look at one of these faces, if you have this triangular force distribution over here. Now this triangular force distribution, it can be converted to an equivalent force over here, right? It is just how you make equivalence of uniformly distributed load, triangular loads, and so on. It's exactly similar. So you have this triangular force distribution, for which maybe this is the equivalent force that you have over here, and as you can see, since it's triangular, it acts at 2/3 from here, but that's irrelevant in this context. So, and similarly you have for the compressive part, both as the left side as well as the right side over here. Okay, so this is the overall element equilibrium, because remember, the element is neither traversing to the left or to the right. It is somewhere still within the beam, so the forces must be in equilibrium, right? What you see here in this figure, so maybe I will mark this figure as number 1 and say this is my number 2. Number 2, the figure number 2 is nothing but the cross section of this one over here. So remember that these derivations, both what we did for the bending and what we are going to do for the shear, it is not just valid for rectangular cross section, it is valid for any general cross section as long as your section is prismatic or your beam is prismatic, that is, the section is same throughout the entire length of the beam. Right. So now this is the cross section. So this is how the cross section of the beam looks like, sort of an oval shaped egg kind of a thing, if you want to consider. Now, so this one has this length dx over here. So this is the cross section. Now within this cross section, to write the equilibrium equations, I am looking at a small element, so anything above. So I have taken a section of this smaller chunk which I have separated of the beam. So let's say this is the section I am looking at. Right, so anything over, so I am going to consider, I'm taking a small chunk which is this top above this red rectangle which I just drew, this top chunk over here. For that I am going to write the equilibrium equation. Now before writing the equilibrium equations or seeing the forces, let's see the different parts of this figure. So as we already deciphered, this is a length dx over here. Now where I have taken this section, this line, it has a distance of y prime from the neutral axis. This top chunk that is there, that has an area a prime, and the centroid of that area is at a distance of y bar prime from the neutral axis, and all of these parameters will come into play, and that's why we are essentially looking at it, right? So this is the section plane, so it is written the section plane. So above the section plane, the area is a prime and the distance is y bar prime over here. Okay, now if I take this section over here, right, and I am just deriving the equilibrium for this section. Remember, this section is also in equilibrium. The whole beam is in equilibrium. This small chunk we separated, dx is in equilibrium. Within that small chunk, each of the smaller chunks also in equilibrium. And equations of equilibrium is valid anywhere, whether the smaller chunks, the bigger chunk, or the entire beam. So I am going to separate out this top small chunk over here. That is the part element that I am calling the part element, which you see over here in this figure. So this is, say, maybe my figure 3, right? So this is the part element that you're looking at, and I'm looking at the equilibrium for that. This is shown in 3D over here, from directly taken from here. Okay, now once you take this guy over here, let's see what are the forces or the stresses which are acting. So on this left hand face, which is this face over here, let's say the stress is sigma, right? The sigma, remember, is my divided by I if the moment is m. And here on this particular side you have the moment m plus dm, so the stresses will be different than here on the left side. So this one is known as the sigma prime over here, right? Okay, are these the only stresses which are there? Probably not, because you see these two are different. This sigma and the sigma prime are different. The area of the area of this part element, say, is same in both the sides because it's prismatic. So it's a prime here as well as a prime over here. So what is this additional force which is balancing, which is keeping this part element in equilibrium? Well, remember, don't forget that across this face you had the V, which was that transverse, which was that transverse shear which was acting, and in addition to that you also have this complementary tau over here. So for this tau over here, I should not say V, I should say tau. For this tau you have a complementary tau which is acting over here. So as you can see at the bottom face of this element over here, you have this stress which is tau which is acting over here. Okay, so we have sigma, sigma prime, and the tau, and all of these are kind of working together to keep your overall element in equilibrium, right? Okay, so this is the 3D figure. If you look at the 2D, just to make it simple, so this is the 2D representation of this. This is the tau. This is more clear in this figure over here. This is tau which is acting at the base over here, and this is the element length is again dx. So let's just mark that over here. So this is again dx, right? And then on the left you have your sigma, and on the right you have your sigma prime that is there, right? Okay, so now either, and let's call this figure number 4. So either from figure 3 or figure 4, if you start to write the equilibrium equation, what do we get? So let's maybe look at this figure over here, while acknowledging there's a tau which is acting at that section phase. So if I have to write the equation of equilibrium, that my summation of fx equals to 0. For this part element, I am just writing the equilibrium equation that is there, right? So first let me write out the equation, and then I will explain the different terms. Essentially I am doing a balance of the forces that is there. So what we have over here is that, so the equilibrium equation tells you that here in this particular equation that we have, this one is the force which is acting on the left face, on this left face over the entirety of the left face that you see, that is sigma is the stress. I'm multiplying with a small element dA prime that is there, and integrating over the entire area A prime, right? So this is this force. So I have considered this direction as positive. So let's say this is my positive x over here, or in this case this is positive x, right? So tau is also acting along the same direction, and what is the force due to tau? Remember, this tau is acting over this dx, and this thickness that you see, the thickness of this particular element is this t over here. So how to get force from stress? It is stress times the area. So the area of this section plane is t times this dx. So tau times t dx minus of this of the force which is acting on the right hand face. So that is integral of sigma prime dA prime A prime with a negative sign. So this whole thing is in equilibrium, so it must equate to 0 over here. Now what we just discussed, or what have you learned in pure bending, that this sigma is nothing but your my divided by I for this left hand face, and for this right hand face this sigma prime corresponds to m plus dm. So it is going to be equal to m plus dm times y divided by I. So you see that before we start writing this down, that this is where you start to have the interconnections between the moment and the shear. We are exploiting the things we have learned for the moment to get the shear, right? And one very important thing is that this shear actually exists only because the moment at the two faces are different. Remember when we talked about pure bending, remember that pure bending where both the faces were M and M. What was pure bending? The case where shear is 0. So if you have M and M both the same, that is, if this M over here and here also, instead of M plus dm is just M, your tau essentially vanishes, right? So for pure bending you did not have shear, but when you have these bending stresses or the bending moments different at either faces, then only you're going to have shear. So this shear, what you see, is actually induced by the moment that you have in your structure. So let's go ahead and express the sigmas in terms of your M by My by I, and then see where this leads to. So let me write the next step of the equation. So what I have done here, I've simply expanded the sigmas in terms of, M over here and sigma prime as M plus dm. So now let's pull things out of the bracket, cancel a few things, and see how far it further simplifies. So this is the next simplified step which we just wrote over here. As you can see here, this term and this term are similar, so they can cancel out. And once we cancel out, what we get is, so we get to this step over here where tau times t dx is equals to this one over here. Let's go ahead and rearrange a little bit more. So tau becomes something like this over here, that is dm dx times 1 divided by I, which is the area moment of inertia of the whole section. Remember, it is of the whole section, because we have written sigma equals to my by I, and when we had derived this for pure bending, this I was for that entire section over there, times t, that is the thickness of this beam section at that point over here, right? Integral of a integral over the entire area of a prime times y times dA prime, that is there. Now what do we know by dm over dx? Remember, go back to your roots where you derived the shear force diagrams and the bending moment diagrams. The derivative of the moment is equals to the shear. So you see that is where the shear V comes into play. Remember, dm over dx equals to V. So let's just go ahead and write that as well. So tau becomes equals to V, that is the shear force at that particular section, divided by I times T integral of this one over here. Now this particular thing that you see in within the integral over here, if I represent this by something else, and I'm going to call that as Q, so equals to Q, where Q, let me just rewrite that, Q, where Q is integral over a prime y dA prime, then this equation further simplifies to tau equals to VQ divided by IT. Let's circle that. Let's put a important rectangle over that, right? So tau equals to VQ divided by IT, and this, my friends, is the shear formula. Now, a couple of things. Let's now dissect this equation and see what all we have. So tau equals to VQ divided by IT, where V is the applied shear force that we have, right? So that is clear. Let's go to the denominator. I is the area moment of inertia of the entire section. This is important, for the entire section. T is the thickness of the beams. It's a prismatic beam and may not be rectangular, it may be this shaped or some other shape. So T is wherever you're calculating the tau. See here, this tau, remember we're calculating here. And why are we calculating the tau here? Because remember at that particular point, this tau is actually the tau which is going to happen over here because of complementary, remember? So here, this tau that you see over here is going to be actually, it is going to be equal to, and I'm just going to draw it with a small line, will be equal to this tau that you will have at that particular interface because of complementary. We'll come to that in a minute, right? So I and then we have the T, which is the thickness of this one over here. Okay, the last bit which is remaining in this equation is this Q. Now Q is an important terminology, and it is essential to understand this because it will it can make your life quite easy depending upon how you want to calculate that. So Q is integral over of y times dA prime that you have over here. So that is what that means is that it is the area moment. So this is the area moment about the neutral axis that you have over here. So this Q can also be represented as the area of this chunk times the distance of the centroid for this chunk, which was y bar prime, to the neutral axis that you have over here. So this Q I can further simplify and write it as equals to y bar prime times A prime, right? So it is the area, it is the product of the area above the section you are looking at times the centroid of that area from the distance of the centroid of that area from the neutral axis. Now, a very interesting observation you see is that for this section, and when we had derived pure bending, remember that how did we prove that the neutral axis coincides with the centroid? How we proved that we had that particular thing was that your integral of y dA was equals to 0 for the entire section. This is how we proved that your neutral axis coincides with the centroid. Now look at this formula for the Q over here. For this one, what I am saying is that it is the moment of this area about this particular neutral axis over here. Now since the moment of this entire area about the neutral axis is equals to 0, and that led to the neutral axis being at the centroid, to calculate Q you can either consider the upper half or the bottom part over here, because both of it has to add up and give it to 0, because for the entire cross section this must be equals to 0 over here. So Q, to calculate Q in this one, what I did, I took this area times the distance from here to here. Instead of doing that, what I also could have done, I could have taken this bottom chunk over here, this bottom chunk. No, instead of this top chunk, I could have taken this bottom chunk, calculated the area of that one times the distance from the neutral axis to the centroid of the area of the bottom chunk. So either you take this upper chunk over here or the bottom chunk. You cannot take both, because if you take both, then eventually that because the neutral axis passes through the centroid, it is going to be 0. A few examples will make this concept slightly more clear, right? So overall, I hope you understood what is the shear formula. Now let's see through some easy to observe sections that how to calculate these different things which are there. Before going into the different sections, as I said, let me bring you back and reiterate the shear formula. So this is what we looked at, that tau equals to VQ by IT, and this page essentially has all the necessary information. This will be in your uploaded slide as well, so you might want to take a look later. So here you see what we did, we sort of cheated, that because of we had the shear force V. So this is the V, which is the force which is acting at that particular cross section, and we calculated this tau as VQ divided by IT. But to compute that, we did not use this tau, we used the complementary tau. So this is the tau which we're going to calculate, but what we used was this tau over here, right, which because of complementarity it exists and it is equal to this particular tau that is there. So tau equals to VQ by IT, and remember that again a few things is I is for the entire section, very important. It is not for just the small chunk that you are looking at. I is for the entire section. T is this width or the thickness of this section that you have, the width of the cross section that you see at that particular point where you are calculating the tau over here. And lastly, the important thing which we discussed, that this parameter q, you see it is described here as well, that it is y bar prime times a prime, that is the y bar prime times a prime, where this is what I was saying, a is the area of the top or bottom, because your integral of YDA for the entire section is 0, so it must be equal and opposite what you get, of course with a modular sign, that you can tell that that it is the area of the top or bottom portion of the member's cross section above or below the section plane where the T is measured. So if this is your section plane, it is either the area of the top, you take this a prime times y bar prime, or you consider this area at the bottom and the distance from the neutral axis to the y bar prime of the area which is at the bottom over here. Now let's go ahead and look at some of the sections and how to calculate these things essentially. So these are essentially some of the examples again for calculating the q, because the q is important in some cases and there will be some problems in which taking the bottom part is easier than the top part. So okay, so here you see in this case, so this is the the neutral axis of a beam over here, right? And you are, suppose you are calculating the shear at the point P, right? So this is the point P that you see. So for to calculate q over here, how will we calculate? So this is above the point P, means you're calculating this area of cross section that you see. So let's just let me go ahead and maybe mark that. So this is the area of cross section which is your a prime over here, and the distance of the centroid from the neutral axis y bar prime, which gives you this formula over here. Similarly here, this is your point P, and in this case this is your area of cross section, and this is the distance to the neutral axis of the centroid for this one. And the last one, see, this is the last, in this one it may be easier to calculate the q from below, although it is not shown here. Here if you're calculating the stress at this point P, now here the stress here and the stressor will be same because it's a symmetry, it has a centroidal axis of symmetry over here. But anyway, regardless, so to calculate the q of here, you can separate this into two chunks. This is essentially how you calculate centroids of section and so on. So you can consider this area, that is your A2, and because of A2 the distance of this one is y2 bar prime, and you have two smaller areas over here. So you essentially are taking the whole area above this line of this line which is parallel to the neutral axis that you have over here. So you are taking these two areas as well. So that is your it is not marked over here. So this area is your A1 prime times your this distance, and twice because you have two chunks over here, one on the left and one on the right. Now this is also an example where instead of going above the neutral axis and considering this area to calculate q, you could have considered this and this as well. So essentially you could have considered your point P, in this case lies exactly on the neutral axis, so you could have considered this one as well, right? Similarly for here, for this one, instead of taking this area, and here sorry, before moving on to this one, here it will be easier to calculate, well, marginally easier, because you just have two identical rectangles over here. See here also, instead of, if this is your point P, instead of taking this area over here, I could have very well taken this area times whatever, say the centroid of this area is over here. Let me mark that, right? And I would have just have to take this distance over here for the distance to the centroid of that particular chunk of the area that is there. So I hope that this is overall clear that this is the most important thing, the shear formula, that tau equals to VQ divided by IT. Take a notebook, write it down 5 times and you will understand what I'm talking about. And once we have this, let's go ahead and solve some problems. We'll look at one very simple example and another slightly involved, where you have to make use of a shear force diagram. Remember that similar to, remember for bending, when we did, your sigma was maximum where it was maximum in the beam. It was within a section, it is always maximum at the top or at the bottom, but within a beam it is maximum at the point where the bending moment is maximum. Similarly, tau is maximum at the point where your V is maximum. So essentially you have to find the the place within the beam from your shear force diagram where the V is maximum. Typically it occurs where typically at the sections, remember, typically at the supports, I mean not the sections, that where your shear forces is pointy shear forces at the supports, at the roller or the pins are the maximum over here. So let's go ahead and look at a few examples of first of a simple section of how to calculate the tau for a simple section given the V, and then of a beam where you have to calculate where the maximum V occurs and then calculate the tau. So this is the first example problem that we are looking at, a simple problem. So what we have in this problem, this is just to get the ball rolling on how you punch in the numbers and how you get the things. So here in this example problem, you have essentially a circular cross section, a solid tube. So it's completely solid, and you're given the radius C equals to 50 mm. Now at this cross section, this may be a part of a beam, and at this cross section, you're having a shear force of 4 kilonewton that you have, right? What it asks you is to calculate the shear stress tau acting over the horizontal diametric line. So let's just go ahead and mark that horizontal diametric line. And so what the problem is essentially asking you is to calculate this thing over here. Right? So say this is passes through the centroid and in neutral axis and all that. In this case, especially in this case, because it's a a circular uniform cross section that you have. So what you are asked to calculate that about this line, right? What is the value of tau that you get over here? What is this tau essentially that you get? So that's the question. So this tau is supposed to be found. So you're given all the data and everything, right? Okay. So now that we know that for the tau, let's just write our basic equation that we know that, and now you're also given a hint. This is just to help you out, although you should know to derive these things. Remember that for and we will see where this hint comes into play in this problem. So we know that from our shear formula that tau equals to VQ divided by I times T. Right, so we already know this guy over here, that tau equals to VQ divided by IT. So now let's just plug in the different numbers. So we have in our case that V is 4 kilonewton, so that is 4000 Newton. I'm writing in Newton mm so that in the stress I get in MPa at the end. Let's calculate Q. Q, remember, for Q we either have to consider this area and the center distance from this or this one. It really doesn't matter in this case. Nothing is going to make you help you out even more because it's circular and it's symmetric, top at the bottom. But Q, remember, is the area of the chunk which you're looking at. This is the top one, and the distance of the centroid of that chunk from the neutral axis. So the area is going to be, so since the radius is 50, so the area of the entire circle is pi c square. So the area for this is going to be, so I'm just going to consider this part. So for this Q is pi c square divided by 2, because half of the circle I'm considering, times the distance of the centroid for this one. So let's say the centroid lies somewhere over here. So this distance, that is given as 4c by 3 pi from the base. From the base means I'm calculating from here. So from the base, this is 4c by 3 pi. So let's put that forgot to change the color, 4c by 3 pi. We have calculated that. Now I is for that entire cross section. Always remember, I is always for the entire cross section. So I is for this circular cross section is pi c raised to 4 divided by 4 in terms of the radius, right? And lastly, my width, right? That width where I'm calculating, this is this guy over I'm calculating here. So it is this guy. So this is your the overall length that you're talking about. This is T. If I was calculating this at a slightly higher, then your T will be lesser. In this case, T is equals to the diameter, that is 2 times the radius. So T is 2 times C over here, right? So if you take all of these and if you plug this back in this formula over here, what you essentially get is your tau becomes equals to 4000 times pi times 50 square divided by 2, right? times 4c by 3 pi. So 4 times 50 divided by 3 pi. So if you plug all of these values in and punch in your calculators, you will get tau as equals to this. I have calculated already, 0.68 MPa. So this is your answer. Simple problem, right? Now, if let me ask you something. Now, instead of this being a solid cylinder, what if I gave you this one? What if I gave you this hollow cylinder? So similar, you have a 4 kilonewton load, the radius is 50, but it is hollow now, so it's a hollow beam for that matter, and the inner radius is 20. So it's the same thing. So again, for this one also, if you had to calculate about this horizontal diametric line, which is this guy over here, so your tau in this case is restricted, of course, to the solid part. The hollow part cannot have a tau. So what is going to change in your, so your formula still stays the same, VQ by IT. So the only things which are going to change overall is that your Q is going to change in this particular case, because now you have to consider just your this area over here, right? Your I is going to change, your T is going to change, and so on. So if you compute that for this one, please try to calculate for this problem. So for this one you will get, and I've calculated this, please work it out on your own. For this one you will get 1.09 MPa. And this number is actually higher than this one over here, because here you see you got 0.68 is 1.09y, and it logically also makes sense because here you have lesser beam material to resist the same amount of shear force, so automatically your stress is going to be higher. So I hope this problem example was clear. It was a simple problem example where you were given a section and the force and you were calculating the tau. Next we'll look at a slightly more complicated example of a beam cross section. So this is the second example problem, and I want you to observe this problem carefully because it essentially deals with beams, and these are the problems which are more relevant for you at this particular point in time. So what you have, if you take a look at this problem over here, is that you are given a beam for which, now it has many things, so let's just go step by step. You are given a beam, a simply supported beam, pin support and a roller on the other end with a 6.5 kilonewton meter UDL over here. Okay, and what it says that the beam is made of two boards. So you have a board 1 on the top and the board 2 at the bottom. So let's just quickly mark that over here, right? So this is B1 and this is your B2, board 1, board 2 over here. And as you see in this cross section as well, this is essentially the top board and the bottom board over here. I will come to what this black dot in between is. So here also you have this is your B1, and this one is your B2, and if you look in 3D, this is your B1 and this is your B2 over here. Okay, now what it says is that determine the maximum shear stress, that is the tau, in the glue necessary to hold the boards together. So these two are separate boards which are joined at this interface over here with glue. So this is where your glue is. So your glue essentially is about this particular interface running the entire the length of your section over here. So if I have to explain this, so maybe it is something like this over here. So you have or the other way around. So you have the top one which is wide, and then at the bottom at this interface you have glue, and which is stuck to the bottom one over here, right? Okay, so it says to find the maximum shear stress in the glue. And why will the glue have a shear stress? Because remember what we had seen, that if you had wooden planks which are not glued together, and if you are putting the force, they simply slide from one another. So the job of the glue is to resist the shear, and this is again the longitudinal shear, which happens as a consequence of the transverse shear because of the complementarity, and all this by now, right? So so this is the plane of the glue. See, this is the bottom board, this is the B2 over here. So at this interface between the B2 and the B1, so this is where your glue is. So your glue is essentially here, okay, all running all across the length of the beam. So for convenience, you are also given the following, that y bar, that for this cross section, so this is the cross section of the beam. So for the cross section, you're given the y bar. So this is the distance of the neutral axis from the below, or distance of the centroid from the below, because the neutral axis, because it's made of one single material, maybe both woods are the same. You have neutral axis passes to the centroid. So this y bar is given as 120 mm. So let us make a note of that. So y bar equals to 120 mm. Right, and also you are given the area moment of inertia of the entire section, again very important for this entire section that you have. And also it says that you can easily calculate. This is what I have written for you, because in the problem example, if you refer to the book, this is from your Hibbeler's book, that you have to go ahead and calculate, but now you know how to calculate this, so I'm not going to go into the details of this, right? So now coming back to the problem, now your problem is clear. You have a beam with loads. A beam, the cross section is made up of two boards, and these boards are joined at the interface over here with this glue. So the problem asks you the maximum shear stress in the glue. Now this glue, which runs throughout this beam, is going to have shear stress everywhere at every point. But where is it going to have the maximum shear stress? You are right, it is going to have the maximum shear stress in those sections, and in adjacent to those sections where you are going to have the maximum shear force. Now in a beam with some loading, how do we find where the maximum shear force happens? Correct, again we find from the shear force diagram. So essentially, for this given beam with this support condition and this UDL, you have to first draw the shear force diagram of the beam, find out where the maximum shear force or the maximum V occurs. So that is what we are trying to find first. So we are trying to find where in this beam this max V occurs, and this is the place where your tau max will also happen at that glue, because the maximum V will give rise to maximum transverse shear and complementarity, and from complementarity you will have the maximum longitudinal shear, which is resisted by the glue, because longitudinal axis means along this axis over here. Okay, so what I want you to do now is this: for this beam, please go ahead and draw the shear force diagram and come back and check whether the diagram which you have drawn is correct or not. So this is the shear force diagram. I hope you have got it correct. So this is how the shear force diagram looks like. So as we expected, the maximum shear force happens at the support, and the value of the maximum shear force over here is 19.5. So from here you can say your reactions are sort of going to be pointing vertically up, of course. So the shear which you have marked over here is correct. So it is in the vertically upward direction, which you can see here as well. So it is that V comes out as 19.5 kilonewton. So let's make a note of that. Okay, so now that we have this over here, now our job is to find the maximum tau. So in this whole beam that you see, in the whole beam, the maximum tau is also going to happen somewhere over here, just adjacent to the support, because this V gives rise to this tau over here. So this tau, so since this V is the maximum in the entire beam, let me just maybe go ahead and call this guy as V max. So at the end, at this edge over here, if this is your beam, so here this tau, because of this V, is going to be tau max at the glue. So I'm writing the max at the glue, not the entire section. This is the where it happens at the glue, right? Because the glue runs along the length of the beam, and this is also tau max, right? So how do we calculate that? It's again very obvious. We know that our tau max, so I'm going to simply write tau max equals to VQ divided by I times T. So remember, this maximum we are calculating at the at the glue interface. So at the plane at the plane containing the glue. So let's just plug in the numbers and see what we get. So what we will get is that your tau max, your V is 19.5 kilonewton. Now to calculate Q, so Q is an important quantity to calculate. Now Q, remember, is what Q, so we are considering this interface over here. So that means I am going to consider this area over here. You can consider the bottom one as well, and you will see that you will get one and the same thing essentially. So if I just consider this top part over here, so for calculating Q, I am going to consider this part. So let's just go ahead and calculate for here. So for this, what we will get, I will write it in the bottom part. So Q, I will get the, what is the area of this part? It is 150 times 30. Remember, the basic formula for Q is your y bar prime times a prime, where a prime is the area of this one and y bar prime is the distance of the centroid of this one. So if the centroid of this guy lies somewhere about here, it is essentially the distance of that from this neutral axis. And in our case, what does that distance come out as? Let's see. So my total is 180, 150 plus 30, out of which 120 is gone. So that means the remaining distance that I have, that is from here to this total top over here, this distance is 60 mm, right? And I'm calculating the distance from this neutral axis again, not to the top, but at the center, right up to here. So it will be 60 minus half of this thickness of the board that you see, that is 60 minus 15. So this is going to be 60 minus 15, so that is 45 mm, right? So this one here is going to be times 45. Okay. And if you, as I said, if you take the bottom part, if I, instead of taking that one, if I had taken the bottom part, that is if I had taken this chunk over here, right? Now one important consideration before I go to the bottom chunk over here, you see that at this particular point I took this Q as 150 times 30 times 45, where 45 was this distance from here to the centroid. Remember, it is not to the top or the bottom, it is only to the centroid. Now coming to this, if I am calculating the Q from this bottom part over here, let's see what we get. So if I calculate from the bottom part, so I am going to write this as, or for the bottom part, you see the area is 30 times this height 150 times the distance from the neutral axis to the centroid of this bottom part. So for this bottom part, maybe the the centroid is somewhere over here, so that is at 150 divided by 2, that is 75. So and this is at 120 minus, so I'm trying to calculate this distance over here. So it is 120 minus 75. So that again is equals to 45 mm. So equals times 45 over here. So it's the same thing. You get the same thing whether you consider the top part. This is also a proof that eventually you get the same guy. Okay, so this is what we have. So let's just go ahead and fill this one as well. So this is 150 times 30 times 45. So what we wrote, this is my V, this is my Q, and then so this is divided by, and I'm writing everything in Newton and mm, divided by I times T. See, I is given over here, so I, let's just write, so it is 27 into 10 raised to minus 6. Since this is in meter, if I have to convert to mm, is going to be into 10 cube raised to 4, because it's meter raised to 4, times the width. Now this is where it is important. The T remember is the width of the beam which we're looking at. Now what is going to be T? Is it going to be this 30 mm or is it going to be this entire width of 150? So that is an important question. So what is T going to be? Remember, here I'm calculating just at this interface, so that is just above or just at the interface where the bottom board ends, because the bottom board is connected with glue to the top board. So just at this interface, if you calculate, your T becomes equals to this 30. So suppose if I was computing the shear somewhere above in this upper board over here, then the T would have been the whole 150 over here, right? Now this glue is attached just above the bottom board, so by T, the controlling T is going to be this 30 mm that I have over here. So times 30. Now if you plug in the numbers over here and substitute the proper units and so on, the value of tau that you're going to get, I have this worked out already. So the tau max which comes out as is this is the maximum shear stress. So tau max comes out as 4.88 Newton per mm square, that is 4.88 MPa. So this is how we solve this problem. So there are two important things to remember, to take away messages from this problem, is that when you are given the beam with a kind of a loading, you have to find first where the maximum shear force is acting, right? That is the region, and in between that, those sections are the places where you're going to have the maximum shear stresses as well. And to calculate the maximum shear stresses, we calculated the Q either to the top or at the bottom, because both of those gave us the same thing. And lastly, the important point to note is that width T. So the width T, in this case the controlling one, is just at the interface, calculating the plane at the plane of the glue, and the glue is applied just above where the board 2 or the B2 ends. So we took the T in this case as a 30 over here. So I hope this problem example was clear. We will do some more examples later for beams with under different varying loading conditions with different cross sections, for which you will calculate the shear stresses.